Cheese. Cheese. It's okay. Sharon will end it, right? Okay. The higher level part of acids and bases are quite a bit harder than the standard level. Okay, so a lot of calculations are involved and there will be a lot of parts to it. Okay, the first thing is about calculations of acid involving acids and bases. First, we will start with ionic product of water, Kw. Okay, so you need to explain that in itself, okay, when water is left, it will ionize to H plus and OH minus. Okay, and we will relate this to chapter 7, equilibrium. So if students should be able to come up with the Kc expression of this reaction. Okay, this will be just H plus over multiplied by OH minus concentration. We'll ignore the water concentration because it's different phase from the rest. Okay, different state from the rest. So Kc is like that, but in this case we give it a special name, Kw, for ionic product of water, but it's actually just the equilibrium constant of this dissociation. So it behaves like an equilibrium constant. It stays constant at the same temperature. Okay, and the students need to know that at 25 degrees Celsius, this is equal to 1 times 10 to the power of minus 14. Okay, and then because we know the concentration of H plus and OH minus in pure water is always the same, from here we can calculate that the H plus concentration is 1 times 10 to the power of minus 7. Okay. Okay, and because of that the pH is 7. Okay, but this one is only true at 25 degrees Celsius. Okay, which means at 25 degrees Celsius the pH of pure water will be 7. Okay. Next, you need to explain the effect of changing temperature to the pH of water. Okay, so this one again will relate to the previous chapter, equilibrium. So students should be able to deduce that the delta H of this dissociation will be positive or endothermic. Okay. So because of that, when we increase the temperature, increasing temperature based on the Le Chatelet's principle will shift the position of equilibrium to the right, okay, such that you will have a higher concentration of H plus and higher concentration of OH minus, okay. So the H plus concentration will be greater than 1 times 10 to the power of minus 7. So because of that, the pH will be less than 7. Okay, of course the next question that follows will be, does it mean water at higher temperatures is acidic because the pH is less than 7? So here is where we will place their concept, okay, their previous concept about using pH as a measure of acidity, okay. So now we will say that even though the pH is less than 7, but because the H plus concentration is still equal to the OH minus concentration, water is still neutral, okay. So we define something as acidic only when the H plus is greater than OH minus, and when we define something as alkaline only when H plus concentration is smaller than OH minus concentration. Okay, so again, even though at higher temperature pH of water is less than 7, it is not acidic, it is still neutral. Okay, so this is something that you have to explain to your student. Okay, so we already discussed earlier that pH is equal to minus log concentration of H plus. So here we are introduced to a new key is POH, which is the minus log of OH concentration. okay? Based on the Kw equation, okay, if we do some math and take negative logarithms of this expression, you'll get pKw is equal to pH plus pOH. Okay? And because we know the value of Kw at 25 degrees Celsius, we know that at 25 degrees Celsius, the sum of pH and pOH is always 14 at 25 degrees Celsius only. Okay, so that's about the ionic product of water. Your students also need to be able to solve simple questions like finding the pH when you know the H plus concentration and stuff like that. Just need to apply this equations, okay? But there is one thing that you need to take note about, okay? Take note of. It's about the pH of a very low concentration of very dilute acid. Okay, for example, if I have HCl, okay, when the concentration of is 0.1 mole per dm cube, I know that this will give a H plus concentration of 0.1 mole per dm cube. And when I use my calculator and take minus log of this value, I know that the pH is 1. Okay? But for example, if I have a very, very dilute HCl concentration, 1 to the power of minus 8, for example, mole per dm cube. Okay? So when I take, because this is a strong acid, I know that the H plus concentration will also be like this, okay? But if I use my calculator and punch minus log to this value, I will get 8. Okay? So this is an acid. So can the pH of acid be greater than 8? I mean, be greater than 7? The answer is no, okay? Because this is very dilute. Okay, usually when we calculate all these things, we ignore the H plus concentration from water because it's very, very small. 1 times 10 to the power of minus 7 compared to 0.1 is really small, so we ignore it. But when the H plus from the acid is really low, the H plus from water becomes significant. Okay? So to simplify it, okay, we can just add them together. By right you can't, because the addition of acid will disturb the equilibrium. Okay, but just as an illustration, so you have like 1.1 times 10 to the power of minus 7. Okay, when you take this, the minus log of this value, it will definitely be less than 7. Okay, so which means at 25 degrees Celsius, the pH of water, the pH of an acid can never be greater than 7. Never. Okay? Now we'll move on to weak acids and bases. Okay, so let's use acid as an example. CH3COH, okay? This is a weak acid. Reacting this with water will result in okay. Again, we'll deal with equilibrium. So this is an acid. If I were to find the Kc expression or the equilibrium constant expression of this reaction, it will be product, concentration of product at equilibrium multiplied by the H plus concentration. I'll just use H2O plus and H plus interchangeably. And CH3COH. Okay, so this is the equilibrium constant expression of an acid, but I will, because it's a weak acid, we give it a special name, Ka, okay? It's called acid dissociation constant. Now, what is the use of this Ka, okay? If you realize again, Ka is giving you the ratio between the product, which is the dissociated form of the acid, over the reactant, which is the undissociated form of the acid. And if you know the definition of a weak acid is that an acid that doesn't that dissociate only partially in water. Okay, so when you look at this value, is a ratio between the dissociated form and the undissociated form. Okay, So if the extent of dissociation is greater, you will end up with a higher Ka. Correct? Because when the Ka is higher, you will have greater dissociated product. So when the Ka is higher, the acid is stronger. Okay? When Ka is lower, acid is weaker. Okay? Then we also need to come up with this new concept, pKa. pKa is minus log of Ka. Again, is a negative relationship. So when Ka is higher, acid is stronger, but the pKa will be lower. And Ka is lower, acid is weaker, but pKa will be higher. Okay? Just something that you need to know what Ka is. So again, just like any equilibrium constant, Ka is constant at a certain temperature. Okay, and the value of Ka is of many acids and bases are given in your data booklet. So what's the use of this? You can use this expression for two things, okay? One is calculating the pH of weak acids or base. Okay, so of course if you're using base, you will use Kb, which is the equivalent expression for bases, okay? Second, you can use this to calculate pH of buffer solutions. Okay, so we'll discuss the second method in the buffer solutions equation. Okay, so a sample of questions that can be asked, of a question that can be asked in this part will be, they'll give you a concentration of a acid, for example, calculate the concentration of 0.1 molar of, calculate the pH. Calculate the pH of 0.1 mole of a weak acid. Okay, so this is just a sample of question. We'll discuss it in the question section of the video, okay? Now for buffer solution, you need to define what is buffer solution, okay? And there'll be, you need to be able to calculate the pH of buffer. Okay, so I think there are two methods to this, okay? One is you can use the Ka or Kb expression. And secondly, you can use the it's not this. You can use the what? Henderson-Hasselbalch equation, yes. Henderson equation. Okay, so two methods. Again, we will discuss this in the question section. Should I discuss it now? Should I just cut this part? Can? Oh, it's very long. Okay, off first, then I will start again from this one. And
maybe you can do that on the
question. Yeah? Because for the rest, I never explained so much actually.
Correct.
Because this is what they need to know, right? Yeah. So.
The application will be on.
Yeah, in the question. It's okay. Okay, off anyway. I need to write the